Hey everybody, in this video, we are going to talk more about equilibrium constants. In this reaction, we have a reaction going from a gas to a solid and an aqueous substance. Now what we have to do is write the equilibrium constant, K. So how do we do that? So we will be focusing on our aqueous substances and our gaseous substances, and ignoring our solids and liquids. So let's ignore that solid right there. So to write the equilibrium expression, we do products over reactants. In our products, we focus on C, and since this is aqueous, we will put it in brackets to define concentration. So the concentration of C to the C power, since the coefficient is C, and you divide by the reactants. And for our reactants, we have a gas A, so we put the partial pressure of A in parentheses to the A power, since A is the coefficient, and here is the equilibrium expression for the reaction above. So now let's look at this cool reaction right here. N2O4 is in equilibrium with 2NO2, and they're all gases. So let's calculate the Kp if the equilibrium partial pressures are. So over here, the partial pressure of dinitrogen tetroxide is 0.22 atmospheres, and the partial pressure of nitrogen dioxide is 1.56 atmospheres. Now remember, if you want to plug in pressures into the equilibrium expression, they have to be in atmospheres. And look at that, we have that. So we're doing great, and let's just plug it in. So we plug in 1.56 here, and 0.22 here. And by the way, this is the equilibrium expression for this reaction that I wrote. And simplifying it, you get 1.56 squared divided by 0.22. And your answer has 2 sig figs, so it's 11. And note that K is unitless because activities are unitless. Remember, these things we're plugging in are actually activities and not really pressures or molar or anything like that. They're actually activities, and you can refer to the previous video to learn about activities and why they are unitless. So, we have the equilibrium constant, and note that this is at a certain temperature T, so changing the temperature may change K, but we will talk about that in a future video in the future. So, let's talk about the effects of changing the reaction coefficients on our equilibrium constant K. So, the coefficients in a reaction matter. Changing it changes K. So, the first thing I want you to know is that multiplying the coefficients by a factor will raise the equilibrium constant by that same factor. And when I mean raise the equilibrium constant by that factor, I mean that I'm taking it to a power. So this is best exemplified by doing an example. So we have our original reaction here, and we figured out at the beginning that Kp will be equal to 11. Now what happens if we multiply the coefficients by a factor of 2? So N2O4 will become 2N2O4, and 2NO2 will become 4NO2. What will happen? Well, if we multiply the coefficients by 2, we have to take our Kp to the second power. So our Kp was 11, so by multiplying the reaction by 2, we have to take the Kp to the second power. So 11 squared turns out to be 121, but we need 2 sig figs, so 1.2 times 10 to the second would be appropriate. Now what happens if I go from the second reaction to the third reaction by multiplying by a factor of 1/3? So now I have 2/3 N2O4 becomes 4/3 NO2. What will happen to our equilibrium constant? Well, if I multiplied by a factor of 1/3, then I will take my equilibrium constant to the 1/3 power. So 1.2 times 10 to the second to the 1/3 as shown here. And if you know, taking things to the 1/3 is the same thing as cube rooting it. And doing that, you get that the new Kp now for this new reaction is going to be 4.9. So you might be wondering, why does this work? What wizardry is happening here? Well, here's a cute little proof that I provided. So let's just take a reaction going from A to B, and they're all gases, and the Kp is equal to this, and let's just say that the Kp is equal to 3. Now what happens if I multiply the coefficients by a factor n? So of course, our coefficient originally was A, but by multiplying it by n, our coefficients will be now n times A, and our B will be n times B. So let's write the new equilibrium expression based on these new coefficients. So Kp is equal to Pb to the Nb over Pa to the Na. Notice how you can factor out the n and take it outside of a parenthesis. So I factored it out and I got this to the n power. And notice how this is equal to this. So this is equal to this, and this is 3, and we're taking this to the n power. That means that we're taking 3 to the n power. So in the end, you get 3 to the n as your answer for the new equilibrium constant. So notice how by multiplying your coefficients by n, you're taking your equilibrium constant to the n power. So that's pretty cool. Now let's talk about rule number 2. Flipping a reaction makes the equilibrium constant inversed. So you would take 1 to the k if you flip a reaction. So this is our original reaction, and all I did was that I flipped it. Now, if I flip it, that means our k is inverted. So instead of 11, it's 1 over 11, or when simplified, you will get 2 sig figs, or 0.091 for your new equilibrium constant. And for consistency, let's put P here to indicate that we are dealing with pressures. Now let's prove to ourselves why this happens. So we have the same exact reaction, same exact equilibrium constant, and it's equal to 3. What happens if we flip the reaction? Well, our K will now be flipped, so it would be the partial pressure of A to the A power over the partial pressure of B to the B power instead of before. But if I rearrange this, I could rearrange it as 1 over this, and notice how this was equal to our old K here, which was equal to 3. So all I did was I took 1 over the old equilibrium constant to get our new equilibrium constant. So here I could take 1 over our old equilibrium constant to get our new equilibrium constant. And notice how you could pretend that 3 is equal to this, and since 3 is equal to that, then you could plug in 3 here and you would get 1 over 3 as the new equilibrium constant. And notice how they're just inverses of each other. So that's the proof, and that was pretty cool. Now let's talk about something called the reaction quotient, Q. This tells you the ratio of products to reactants for any system, not just a system at equilibrium. And I'll explain why this is useful later on. The reaction quotient expression is exactly the same as the equilibrium expression, so that's pretty awesome, right? Now, if Q is equal to K, or the products over reactants are equal to those at equilibrium, then that means that the system is at equilibrium. So when Q equals K, then it's at equilibrium. Now what about if Q is greater than K? If Q is greater than K, then there are more products than what is supposed to be at equilibrium. So pretend at equilibrium, products over reactants is equal to K. And in this case, if Q is greater than K, this means that there are too many products on the numerator, which would increase the Q value, and that would make Q greater than K. And too many products would cause the system to lose its equilibrium. And now, as I just said, Q would equal products over reactants. So notice how it's capitalized, indicating that there are more products than normal. And equilibrium doesn't like that, because that's not equilibrium if there are too many products. So for this reason, Q is greater than K. Now the system, just like any system not at equilibrium, wants to return to equilibrium if it can. So the system wants to remove these excess products, so the reaction will move backwards for when Q is greater than K. Now what happens if Q is less than K? well, you can imagine that the opposite would happen, and there are more reactants than what is supposed to be at equilibrium. And since K is products over reactants, too many reactants would cause the system to lose its equilibrium, and now our Q is equal to products over reactants. So notice how I said reactants with an emphasis because it was capitalized. And a larger denominator means smaller numbers. So that's why K is greater than Q, since Q has more reactants than normal, so it would have a larger denominator, which would make Q less than K. Now the system wants to remove these excess reactants, so the reaction will move forwards when Q is less than K. Now let's take a look at this again using some comparisons. So when products over reactants is equal to K, and we have the same amount of products and same amount of reactants, and this is equal to Q, and since K is equal to Q, you can clearly see that there are equilibrium, since the ratio between products and reactants are exactly where it wants to be at equilibrium. Now, what about this, where we have too many products? Now notice how when there are too many products, our reaction quotient is much larger. So I drew Q as a very large Q. While originally at equilibrium, the system just wants to have this many products and this many reactants. But guess what? You decided to put so many products that the Q just became larger than K. And when K is less than Q, there are too many products, so the reaction will go backwards. Now what about when there are too many reactants? Well, normally there are supposed to be this many products and this many reactants. That is a Goldilocks condition. But if you decide to add too many reactants, notice how the Q becomes a lot smaller because the reactants are on the denominator, and because there are too many reactants, the reaction wants to move forward to remove these reactants and react them. So this happens when K is greater than Q. So hopefully that logic helped you out. And now let's take a look at a question. So here is the same exact reaction as before, but now I will give you partial pressures that may or may not be at equilibrium. So you're going to tell me that, and you're going to tell me if Q is greater than K, or if Q is less than K, or perhaps if Q is equal to K. So I have here the pressures in torque, but you have to remember that you have to convert it to ATMs, because your brain should have a red flag going up saying, oh, I can only plug in atmospheres as a form of pressure in the equilibrium expressions, so I have to convert torque to atmospheres, and that is done easily by dividing by 760. So here are the pressures in atmospheres, and now let's calculate the Q, because remember, we don't know if this is at equilibrium or not, and Q allows us to find the ratio between products to reactants at any condition. So that's very cool, and let's apply that. So here is the reaction quotient expression, which is the same as the equilibrium expression, and you base it off of this reaction, of course, and we just plug in numbers. So 1.43 squared divided by 0.722 is equal to 2.84. Now we know that K is 11 and Q is 2.84. So is Q less than or greater than K? Well, of course, Q is less than K. And remember from the previous slide that when Q is less than K, there are too many reactants. So therefore, the reaction will shift to the right to remove these reactants. So before you end this video, let's talk about 3 types of K that you might use. So we have, of course, the generic K, or KEQ. This is literally for anything. But if you want to be more specific, and trust me, being more specific is better sometimes, you can use these 2 types of Ks. Now there are more Ks that we will review later on, but these are the 2 main ones I want you to know. KP is when all substances in the K are in pressure or atmospheres, so this typically happens when you only have gases in your equilibrium expression. Now what about KC? We'll use KC when all the substances in the K expression are in concentrations, and this usually happens when they are dissolved or when they are aqueous, and this is in terms of molar, and KP, or the pressures, are in terms of atmospheres. And before we end this video, I want to go over something that is very important that will be used in future videos. This is called the rule of multiple equilibria. It states that adding reactions to form a new reaction will multiply their k values to make a new k value. Now, let's prove this to ourselves. So let's just say we had two reactions. One of them goes from A to B, and one of them goes from C to D. And I wrote the k expressions for each of these reactions, so k1 and k2 are there. And I merged the two reactions to make A plus C becomes B plus D. And notice how I wrote the equilibrium expression based on the net reaction. And if you notice, the net reaction's equilibrium expression is composed of PB to the B over PA to the A times PD to the D over PC to the C. And notice how this part right here is K1, and notice how this part right here is K2, and you're essentially multiplying them together. So the new K for the net reaction is actually equal to K1 times K2, as proved here. So proof done, and we will use this in a future video, as I just said, so watch out for that. And that's all for this video. I hope you learned a lot, and thanks for watching.